Alright, so for this video, we're going to be talking about how to find areas in less straightforward settings, I guess. So in this video, we're going to talk about how to find the area between two curves. And then later on, we'll start looking at volumes. So understanding, I'm going to go ahead and refer to what we've been doing in the past, which is finding the area under a curve. So just if you recall, we could go ahead and say this curve is f of x, and we'll say that this is a and this is b. So they don't have to be on like nice whole numbers or anything. And so the integral that would represent the area that I just drew would be the integral from a to b of f of x dx. And so this is how we recently have been finding the area underneath a curve. And so we would say the process for this is we would have to take the antiderivative of f of x, and that would give us capital F of x. If you guys recall, with some of our notation, we said the antiderivative of lowercase f we just call capital F, and that would have to be evaluated from a to b. And so that equals f of b minus f of a. All right, and we've been calling this the area under the curve. But what this really means is it really is the area between f of x and y equals 0, the x-axis. So really, even though we've been finding the area under a curve, we've actually been finding the area between two curves. It was just that the second curve every single time was the x-axis. All right, so when we look at the process for finding the area between curves, that just means that our second curve won't be the x-axis anymore, it'll be something else. So I'm going to go ahead and draw a picture now using two curves, and we're still not to the point where we technically need the graph paper. I'm just drawing sketches here. So here's my f of x. Your g of x doesn't matter as long as it doesn't really cross the f of x. And again, I'm going to use a. I'll make b over here this time. I don't know why I drew this so big. Yours doesn't have to be as big as mine. All right, so that's the area that I'm trying to find. That's the area between the two curves. So if we want to think through how we could kind of make like a formula to find this, we could say that the area underneath f, I'm going to go ahead and draw this in black pen. Here's f, so the area underneath f from a to b would be this right here. That's the whole area underneath f. The area underneath g of x, here's g of x right here in red. And the area underneath g of x from a to b is this area right here. So you can see that if I take the area underneath f and I subtract off the area underneath g, then that gives me the area between the two graphs as the result. And so that's how you find the area between two curves, is we're going to go ahead and write this as the integral from a to b of f of x minus g of x dx. So when we find the area between two curves, we're always going to do top minus bottom. So the area under the top curve gives you everything. The area under the bottom curve helps you take away the part that's not in between them. And so your leftover would be the in-between area. We can also look at curves that intersect each other. So let's say we have f of x is like this, and let's say g of x looks like that. And I can say here's a, the first intersectional label is b, the second intersectional label is c. So if I wanted to know what the area between the curves was from A to C, I'd have to break up this interval right here, because if you look at these first parts of the curve, I can see that f of x is on top and g of x is on bottom. But then after they cross at B, then it switches so that g of x is on top and f of x is on bottom. So we need to make sure that when we write the integrals, we write them in two pieces, one to reflect when the f of x is on top, the other to reflect when the g of x is on top. So we just have to be careful to make sure that if the graphs switch places, that we keep that in mind when we write our intervals. So we have f of x minus g of x for the first interval, and that's from A to B because f of x is on top, plus, and then for the interval from B to C, that's a B right there, from B to C would have g of x on top and f of x on bottom. All right, we can also talk about the area between two curves that are not functions. So we can have curves that kind of work vertically instead of horizontally, which I'm sure is going to weird you out. It weirds me out as well. So this one would be like x equals g of y, x equals f of y. And then here we could say our interval from A to B. And there's our area between the curves right there. And so here we would say the integral from A to B would be f of y minus g of y. So if you are doing the area between two curves and you're dealing with a function that's in terms of y, then you go from right to left. So we would say right minus left instead of top minus bottom, because top minus bottom would not apply here. All right, so when we're going through these problems, there's a process that we want to go through every single time. And what you'll realize is that at first I'm going to have you guys do a lot of these by hand, but then eventually we're going to do them almost exclusively in a calculator. And so it's going to be important when you're doing a lot of calculator problems to show specific things. So first, I want you to draw the graph of the functions. The purpose of drawing the graph of the functions is so you can see if they intersect at any point, if one is on top first and then the other's on top, and to know what your intervals are, because sometimes they won't give you the interval. So we always need to have some sort of image of what we're dealing with here. And then if I'm grading your paper, it helps me to see maybe you graphed it wrong or something, so I can see where you went wrong. Second, we're going to write the integral that will give the area. And I'm going to say integrals plural, because it could be one integral if one curve stays on top the whole time, but it could be multiple integrals if they switch places. So write the integrals that will give the area. All right, third, find the antiderivative. And go ahead and put a star next to that one. And then fourth, evaluate. So if you are doing this as a calculator problem, you're going to do steps 1, 2, and 4. And you're just going to let the calculator find the antiderivative and plug everything in for you. If it's a calculator inactive question, then you would have to find the antiderivative by hand. So what I have found is that students get so used to doing these on a calculator that they forget, if they ever have to do it by hand, they forget to find the antiderivative and they just go straight into plugging stuff in. So that's just something to watch out for, especially as we start to use our calculators with these. Okay, so we're going to go ahead and do some example problems just to make sure that we can handle these okay. So for example, when we're going to find the area, between y equals x squared plus 1 and y equals x, on the interval from 0 to 1. All right, so I'm going to go ahead and draw a little sketch of this. So the parabola y, or x squared plus 1 shifts up 1, and then it's just a parabola, normal parabola from there. Oh, I almost didn't give myself enough room. Okay, there's our parabola. And then we have the line y equals x, so that's just slope of 1 and a y-intercept of 0. And we're finding the area on the interval from 0 to 1. Now sometimes they'll tell you what the interval is, sometimes they won't. Sometimes they'll give you like the vertical line x equals 0 and the vertical line x equals 1 and tell you to find the area that's bounded by that region, and then you'll be like, oh, the interval is from 0 to 1. So this one was nice because they just gave you the interval that you're going to use to set up the integral 0 to 1. But just keep in mind that sometimes they really will use other lines and you kind of have to think it through. So now we just need to do that other part where we figure out which curve is on top and which one's on bottom, which is nice and easy for this problem. So we're going to say x squared plus 1 is on the top, x is on the bottom. And so if we were doing this in the calculator, we could go ahead and just plug it in exactly the way it looks. But since we're going to do this one by hand, I'm going to go ahead and simplify it a little bit. And by that I mean I'm just putting it in the right order. Okay, so I'm going to do my antiderivative rules. So that's 1/3 x to the third minus 1/2 x squared plus x, and that's evaluated from 0 to 1. So I have 1/3 times 1 to the third minus 1/2 times 1 squared plus 1. And I'm subtracting off 1/3 times 0 to the third minus 1/2 times 0 squared plus 0. And so I know that this part right here is just nothing. And then for this part, I have 1/3 minus 1/2 plus 1. And if I'm truly doing this without a calculator, then I need to get a common denominator for all those pieces. And I know that my common denominator is going to be 6. And so this is 2 over 6 minus 3 over 6 plus 6 over 6. So I have negative 1/6 plus 6 is positive 5 over 6. And the nice thing about these problems, especially if you're using graph paper, is that you can think about if your answer is reasonable or not. So if I'd gotten like 58 as my answer, then that would not be reasonable. But 5, 6 is pretty reasonable, it looks like. You know, it's about 1 square's worth of area, so that's a valid answer. Okay, example 2. We're going to find the area enclosed by y equals x squared and y equals 2x minus x squared. And here they did not tell us an interval, so that means that somehow in the problem we're going to have to be able to figure out what the interval is to find the area. So there's got to be some sort of boundary that cuts everything off. So I'm going to go ahead and graph that first parabola, because that one's pretty easy to graph. That's just normal. And then for the second one, I have to take a trip back to Math 1 to remember how to graph that one. So here, I can go ahead and factor it and find the x-intercepts. So I have 0 equals 2x minus x squared. I do know that since this is a minus x squared, this parabola is upside down, so that's always good to know. I have a GCF of x. So that means the x-intercepts for this parabola are 0 and positive 2. So x-intercept, x-intercept, so that helps. I know that my vertex is in between those 2 points. It's probably right here, but I'm going to double check it anyway. So the formula to find the vertex is negative b over 2a. Well, actually, we know the vertex is a positive 1. I'm not going to go through that work. We know that parabolas are symmetrical. but we don't know what the y-coordinate is. So I do know that the vertex should be +1 because that's exactly in the middle of those. But to find the y-coordinate to see if that really is the vertex right there, I just need to take that +1 and plug it into the function. So I'm going to say, plugging in 1, that gives me 2 times 1 minus 1 squared, which is in fact 1. And so this right here is the vertex of our parabola. Oh gosh, my drawing wasn't great. Okay, so that means that the area that I'm trying to find is the area enclosed by these two, so that means that's this little piece right here. So a reasonable answer would be some sort of fraction smaller than 1. Now, sometimes, like in here, we can see it's pretty clear that our area should be from 0 to 1, that's where it's enclosed, but it's not always that obvious. And so I do want to show you guys the work that you would do if you were not sure what your interval was, because it's not always whole numbers. Sometimes it's decimals that you really do have to put some work in to find by hand, especially on those FRQs. So what we would do is we'd want to figure out where the two curves equal each other, because that's going to be where they intersect. And so I would take x squared, the first curve, and set it equal to the second curve. And then just do whatever process I need to do to solve for x. And in this case, I'm dealing with a quadratic, which means I need to set it equal to 0 and solve for x by factoring, or the quadratic formula if factoring didn't work. So I'm going to go ahead and add the x squared over here. So that gives me 2x squared. I'm going to subtract the 2x over. So there's me setting it equal to 0. I'm going to factor it now, so I'm taking out the GCF. And so x equals 0 and x equals 1. Those are the two x values where the curves equal each other. And you can see that that's my interval from 0 to 1. So in this problem, that was some extra work we didn't really need to do. However, in some problems, that work would have been necessary. All right, so we're going to do top curve minus bottom curve. So top curve minus bottom curve. And if I was plugging this into a calculator, I could just type that in and be done with it. I'm going to go ahead and simplify this a little bit. So I have a negative x squared and another negative x squared, so that's negative 2x squared plus 2x. And now I can go ahead and use my antiderivative rules. So I have negative 2/3 x to the third plus x squared evaluated from 0 to 1. And so that's going to give me negative 2/3 times 1 to the third plus 1 squared, negative 2/3 times 0 to the third plus 0 squared. And those give me nothing. So I've got negative 2/3 plus 1, which is 1/3. So the area between the curves here is 1/3. And that seems pretty reasonable for the problem that I just did. All right, of course we have to do one with trig. You know, doesn't pay to be scared of trig. You got to be okay with it. So for our third example, we're going to find the area bounded by f of x equals sine of x, g of x equals cos x, x equals 0, and x equals pi halves. So this is like what I was telling you when they, instead of giving you an interval, they give you some vertical lines to cut off the graph. Okay, so we're going to go ahead and sketch a picture of this first. And I know that sine graphs and cosine graphs do a complete rotation of the curve, I guess, from 0 to 2 pi. So I'm going to go ahead and just draw the whole thing because that's what I'm used to. And I know that the y-axis goes from -1 to +1. So there's pi and 2 pi. So a sine curve starts at 0 and it goes up to +1 and then back to 0, and then down to -1, and then back to 0. So it's not perfect, but there's my sine curve. And then a cosine curve starts up at 1, and then goes to 0, and dips down to -1, and then 0, and then back up to 1. Those look pretty good. Okay. And then they said that they wanted our interval, well, they wanted the vertical lines x equals 0, x equals pi halves. So I'm going to say 0's right here, putting a dotted line. And then if pi is 4 boxes, then pi halves is 2 boxes. So they want the area between the curves, which means they want this area right here and this area right here. And you can see that for the first little area, the red curve is on top, which was cos. And then in the second area, the pencil curve is on top, which is sine. So we are going to have 2 intervals to represent this problem. So I'm going to say from 0 to something is going to be top minus bottom would be cos x minus sine x dx, plus the second interval would be something to pi halves. And that's sine x minus cos x. And then we have to figure out what that something is in between where the 2 curves equal each other. So I'm going to say I'm looking for where sine x equals cos x. And I don't have to do much work for this. I mean, I could. I certainly could show a lot of work for this. But instead of doing the work by hand, I'm just going to picture my unit circle. And on the unit circle, I need to think about where my x coordinate and my y coordinate are exactly the same. And that happens in 2 places on the unit circle. It happens at pi fourths, because the x coordinate is root 2 over 2 and the y coordinate is root 2 over 2. And then it doesn't happen at 3 pi fourths. The x and the y are opposite signs of each other. But it also happens at 5 pi fourths, and that's where it's negative root 2 over 2 and negative root 2 over 2. So you can see here that at pi fourths and 5 pi fourths. Those are the 2 places where the x and the y coordinate equal each other. This is not the one I want because it's outside of my interval, and so that means that that intersection was at pi fourths. So I'm going to go ahead and show right here. Now if this was calculator active, you could have graphed these on your calculator and found the intersection that way. Or honestly, if you were doing this, you could guesstimate that it was like halfway between and call it good. Okay, so if I was doing this with my calculator, I could just straight up plug it in at this point, but I'm doing it by hand. So I'm going to go ahead and take the antiderivative of cos, which is just sine, and the antiderivative of negative sine, which is positive cos. We're evaluating that from 0 to pi fourths. And then the antiderivative of sine is negative cos. And the antiderivative of negative cos is negative sine. And we're evaluating that from pi fourths to pi halves. Okay, so I'm going to go ahead and do all the work for this. So this gives me sine of pi fourths plus cos of pi fourths minus sine of 0 plus cos of 0. And then I'm adding to that, I'm going to go ahead and do the other one in red pen so you can see the difference. So this right here I'm doing in red. So here we have negative cos of pi halves minus sine of pi halves. And we're subtracting off negative cos of pi fourths minus sine of pi fourths. Okay. So sine of pi fourths is root 2 over 2. Plus cos of pi fourths is also root 2 over 2. Sine of 0 is 0. Cos of 0 is 1. So I'm just doing a whole lot of picturing my unit circle right now. So I'm going to have to add all those together first. complete all of this, and then I can add it to the red part. So root 2 over 2 plus root 2 over 2 means that I have 2 square roots of 2 over 2. And I'm subtracting off 0 plus 1, which means I'm just subtracting off 1. So I just have root 2 minus 1. Okay, so that's for this part over here. For this red part over here, I have negative cos of pi halves, which is just a 0. And I'm subtracting off sine of pi halves, which is 1. And then I have negative cos of pi fourths, so that's going to be the negative of root 2 over 2. And then I'm subtracting sine of pi halves, which is just root 2 over 2. So I have 0 minus 1, which is negative 1, and then I'm subtracting off, I have 2 of these, so that's negative 2 square root 2 over 2. And minus minus makes a plus, so I've got negative 1 plus square root of 2. Okay, and we're adding these two things together. So I have 2 square roots of 2, and then I have a negative 1 and another negative 1. All right, so just want to maybe double check and make sure I did this right in my calculator. So from 0 to pi fourths, I'm not plugging in the antiderivatives, I'm plugging in the original problem. And always be careful when you're using your sines and cosines to finish those parentheses, because we're not used to writing those out. The calculator puts them in for us. And here we've got sine x minus cos x dx. And then I just want to make sure that that's the same as 2 square root 2 minus 2. And it is, so that's good.